The remainder of this class will focus primarily on using numerical analysis techniques to solve engineering problems. In numerical analysis, many simple calculations are generally substituted for the symbolic calculations you're used to doing when you solve a math problem by hand. With numerical analysis, the goal is to approximate the actual solution to the problem. There are advantages and disadvantages to numerical analysis relative to symbolic calculations. The main advantage is that some problems are simply too complicated to solve by hand, but they can be done using computers. The disadvantage is that numerical analysis techniques are subject to unavoidable errors. Because of the way computers work with numbers, numerical analysis almost invariably introduces errors into the calculations. It's important to realize that these errors exist so that you can appropriately interpret the results of the calculations. This chapter provides an introduction to the unavoidable errors introduced by numerical calculations. First, I'll talk a little bit about the fundamental difference between numerical and symbolic calculations. It's pretty obvious, but you need to really keep the difference in mind. Symbolic calculations include symbols as well as numerical values. For example, a symbolic expression might be the square root of 2 times pi divided by the square root of 3. Granted, this is officially a number, but it's represented in terms of symbols. All the numbers in this expression are irrational and can't be represented exactly in a base 10 numbering system. So symbols are used to represent the numbers, and the expression is exactly correct. Numerical calculations only use decimal numbers to represent values in a mathematical expression. For example, this expression might be a numerical representation of the previous expression. All the numbers here correspond to the symbols here, but they've been truncated to a finite number of decimal places. The numerical expression here isn't exactly the same as the symbolic expression above, since an infinite number of terms in the numbers are missing. So in general, numerical calculations introduce errors which result from the finite precision with which numbers can be represented. So why would we ever use numerical calculations if they're almost guaranteed to be wrong? Well, for one thing, engineers need to deal in numerical values. You can't really give this symbolic expression to a machine shop and ask them to fabricate a plate with this thickness. Machining tolerances guarantee that you can't build anything to an infinite level of precision. So as engineers, our numbers will always have some level of allowable error. In this case, we'd evaluate this expression using an approximation and pass a number which contains an acceptable error onto the machine shop. One problem with numerical calculations occurs when the errors become larger than whatever error may be deemed as acceptable. This usually happens when a long series of calculations that each have a small error are performed. The individual errors can accumulate and become large errors. This is a major difference between numerical and symbolic calculations. Now, symbolic calculations have lots of rules to perform various calculations. You can add, subtract, multiply, divide, take square roots, factor polynomials, integrate, and differentiate symbolic expressions. Numerical calculations, on the other hand, use relatively few rules. Addition, subtraction, multiplication, division, and the logical and relational operators are about it. So, when a numerical calculation such as a square root or an integration is performed, the computer might perform many simple operations in order to approximate the corresponding symbolic calculation. This can result in accumulating enough error that the result is useless. In this demo, I'll be dealing with some pretty small numbers, so I'll switch MATLAB's display to exponential format and display lots of digits. I can do this by typing format long E. Now, to see some of the effects of round-off error, I'll add 2.6 plus 0.2. ANS is 2.8. Now, if I add 0.2 to ANS, the result is, not surprisingly, 3.0000 out to the precision that I can display. But now, if I add 0.2 to ANS again, I get 3.2, then a bunch of zeros, and a 1. MATLAB's accumulated enough error to become noticeable in just 3 additions. The round-off error is dependent upon the particular numbers being used. If I add 2.6 plus 0.6, I get 3.2. Adding 0.6 to that result gives 3.8. Repeating the process gives 4.4. And now if I add 0.6 to that result, I get 5 exactly. As another quick example, the square of the square root of 2 should be 2. So if I multiply the square root of 2 times the square root of 2 and subtract 2 from that, I should get 0. However, I actually get some rather small but non-zero number. That results from the round-off errors involved in the arithmetic. So far, I've just talked in general about unavoidable errors in computing. In the next video, I'll give a few more specific sources of numerical errors, namely how computers represent numbers and how they perform arithmetic operations.